everybody, welcome back. I hope you had a good weekend. I know I did. Let's continue talking about DFAs. A little reminder, our first homework assignment, maybe you've had a chance to check it out, is due tomorrow. The problems are written on the class website, and you should send your answers in to Gradescope due tomorrow night at midnight, so you still got some time. Anybody have any questions about the homework? Not yet. All right, let me know if you do have questions. I would be happy to, you can ask, if you have little questions, ask by email, or I'd be happy to chat by it on Zoom about it. All right, great. So we were in the middle of an example at the end last time. I hope you still have your same piece of paper. I thought actually before we get right down into it, I encountered something this weekend, a Twitter thread which featured something like a DFA. So I thought I'd share that with you. Not the whole thing, but this is just a picture that I got. This was a Twitter thread by one of the lead programmers at Valve Software, which is a maker of fine video games and other things. They made Half-Life and Portal and Counter-Strike, and they also created Steam, which is an online game sort of store, I guess. You can download games. Anyway, part of, I didn't know this about Valve, but apparently part of the way that they program in their games is by making DFA-like things for certain aspects of the game. So this is one picture. He posted a bunch of these pictures on his Twitter account, and I put a link to it from our class webpage if you're interested in seeing these. This is from their latest game is Half-Life Alyx, which is a VR game. But this is a, they don't call them DFAs, they call it a state diagram, which is basically the same thing. This one describes the animation that a certain like monster uses when you're shooting him. This is like a shooty gun gun and when you shoot the monster, it like limps or something after you shoot it, something like that. But anyway, this is the diagram. So I guess this is the start state. I don't know if you can see what it says, uninjured. So this is like the monster before you shoot it. And then there are four outgoing arrows. And I don't know exactly what the arrows correspond to, actions that the player does somehow. But this one says flinched. I think this means flinched right leg. And then this says flinched. No, I don't know. This is like different ways in which the thing gets injured the first time you shoot it, and then you can, from any one of these states, you can shoot it again, and it's injured in a different way. And if you shoot it enough times, it becomes injured this much. I don't really know what this means, but this is the kind of thing. There's some really interesting diagrams. They look kind of cool, and I also didn't know that they programmed in this way, but apparently the animators could because typically the animators who just design the way things look, they're not also programmers usually, but the people at Valve created this very simple system so that the animators themselves could create the diagrams like this, so that in addition to, because an animator wants to not only draw the thing but describe how it moves and that kind of thing. So interesting. I thought it was interesting. So check out those links if you're interested. There's another one, like a very simple one, that describes the sort of the trajectory of gun upgrades. There's like I don't know this game, but apparently you can upgrade your guns or whatever. And there's a diagram that describes, you start with this sort of stupid gun, and then you can upgrade it in these ways, and it becomes this other gun. So state diagrams apparently are I mean, obviously a good way to think about certain things, and also used in the real world. Any questions or comments about that? I thought it was interesting. I don't often see DFAs on my Twitter feed. All right, great. Okay, so let's get back to, where'd it go? Here we are. All right, this is what I was writing. last time. Remember, this was the farmer with the goat and the cabbage and the hyena trying to get across the river. And we were trying to describe this, this sort of simple, common logic puzzle in terms of DFAs. So each of the states, if you recall, these circles here are the states, and they describe some possible configuration of all the characters in the story. And this, they have this line down the middle which represents the river that they're trying to cross. So this is the starting state. I never wrote that before, I guess, but you can write that in now if you like. Put a little arrow there. That's the starting state. This is the scenario begins when everybody is on the left side of the river, and your sort of goal in solving the puzzle is to get everybody to the right side of the river. And we saw last time doing various moves can move you into different things. So remember each arrow here, so the G arrow, for example, means that the farmer takes the goat and goes across the river with the goat. So if you're in this state and you do the G, that means the F and the G move over to the right and the C and the H stay on the left, and so on. I hope everybody remembers where we are, because I want to just sort of jump right back on into it. Any questions before we get it going again? No? All right, let's do it. So we were down here. Let's look at, I think this one is totally dealt with. In this language we're using here, the letters in the alphabet are G, C, H, and N. N means you take nothing across. So let's draw the arrows from this state here. The farmer is on the right side here, and so it looks to me like H is a legal move, and H will go back to this state. We already wrote that in, but G is also a legal move, right? That means the farmer takes the goat back to the left side, and on my diagram so far I don't see the resulting state, so I'm going to make a new state right here. The farmer takes the goat back to the left side. F, G, C on the left, and the H stays on the right. This was G, all right? And I mentioned last time that in this particular scenario, all of these arrows are reversible. That means since I have a G going sort of left to right where I just drew it, there's also going to be a G going the other way too. This is not always the case in every DFA, but in this particular one, it is, just because of the way that the rules of the puzzle work. Whenever the farmer goes across carrying something, he could always immediately go back across carrying the same thing again, and that will always be a legal move. Okay, that was the G arrow. What about, so I'm still trying to draw outgoing arrows from here. Remember, every state, in this case, needs 4 outgoing arrows. I have an H going out, a G going out, so I need a C and an N. Can anybody say, where should it go, the arrow with a C on it from here?
Fail state?
Yes, that should go to the fail state. That's because C is not a legal move at this point, because the farmer's on the other side from the C. So the arrow with the C on it goes to the fail. Unfortunately, I have to kind of cross over here. I'll just do a little sneak on under there, right? Is that confusing? I don't know. Or maybe it's less confusing if I just cross the streams. I usually try to draw my diagrams without crossing the arrows over, but sometimes it's kind of unavoidable. Okay, and one more from here. The N. What should the N do? Is it a fail, or is it a actually go somewhere? What do you think?
Fail.
It's a fail. Yeah, the farmer in this case, he can go back carrying nothing, but in that case he leaves the hyena and the goat on the same side, and that's illegal because the hyena eats the goat. So this one is also a fail, so I'm going to put the N along that arrow also. All right. Okay. How about this? Can you guys, could I give you a few moments and see if you can fill in the rest of the diagram? When I did this, I had 3 more states, so we're almost done. I had 3 more states, so decide for yourself. Maybe start with this one and try and draw all the outgoing arrows from this one. You may have to create new states, but like I said, when I did this, I only had 3 more states total. See if you can fill in the rest of this diagram. I'll give you a few minutes and then we can go over it. I don't know if you're finished yet. I've been doing it slowly myself, so you can check up with how I did. When I filled in the arrows, I discovered that these two branches actually come together after at this point. I hope that you decided the same thing from either of these. In this one, if you do the H, you get to here, and in this one, if you do the C, then you get to here. This same state both times with the G on the left. All right. All right, let's just, I don't know how far you got, but let's just see if we can finish off my picture here. From here, I have the N going back. If I do the, I could do the G here, and that gives me a new state. Actually, this is when everybody's on the right side. If I do the G from there, all right? That's kind of the goal, at least for the puzzle. And then if I do the C and the H are illegal here, right? And this maybe is about it, right? That goes there. There's a G coming back here, and then from this state up here, I think it makes sense to call this the accepting state, right? Because when you get here, that means you have correctly solve the puzzle. So let's put a extra little guy around that. And you still have to draw arrows from the accepting state. In the accepting state, if I do an N, that's illegal because if the farmer goes back, then everybody eats everybody else. And the G, I already have an outgoing arrow G going down. C and H are also illegal from this configuration. All right. So I think your diagram should look something like this. Anybody have any questions about the diagram and how you get this? I know it's a lot of stuff to write down, but this
So
is
for the ending state, when you have the F, G, C, H on one side, why does the nothing, cabbage, and hyena fail?
so because from here, if the farmer say does nothing, then all three of them will be left on one side and they'll eat each other, and that's not allowed.
Oh, okay.
So yeah, like ordinarily people don't think about this in terms of the original puzzle, but the puzzle is your job is to describe a sequence of steps which ends with everybody on the right side. If everybody gets to the right side, but then you decide to do one more step, that's gonna fail probably, unless you happen to do this G again. Yeah. So this is a failure after you solved it, then you messed it up by going back across or something. All right. This is our DFA. This is the biggest DFA we're ever going to do in this class, I think. So don't worry that we're going to do examples like this all the time. Any other questions about this?
Is it possible to have it like a little bit different if it still works?
I'm not sure. I mean, your circles can be like located in different places on your page, but I think this is sort of the only right answer. Or do you have another idea?
I just think I had it a little bit different than what you had, but I still ended at the same place.
You still ended up here?
Yeah.
Yeah. But I think, like, for instance, from here to here, I don't think there's a different way that you could have drawn the diagram that is also correct.
Okay.
So maybe you messed up one of the little arrows. I don't know. Yeah.
Okay.
Yeah, on your paper, where exactly you decide to place the states, that will be different for everybody. But which states they are and what the arrows are labeled with should everybody, there's only one correct way to do it. Can we answer the questions that I tried to ask before? I think I still have this. Big questions. Where's my big questions? Oh yeah, so what are the steps which will lead to a correct solution of this problem? And a more interesting question, how many solutions are there? Is there only one way to get to the answer, or is there more than one way to correctly solve the puzzle? What would you say?
There's more than one way.
Yeah, how can you tell based on the diagram?
Because there's multiple paths that you can take that end up at the final state. So.
Yeah, right. So really, when you're looking at the diagram, you want to think of any path along the arrows from start to the accepting state is a solution to the puzzle. So this diagram here will describe all possible solutions, and basically any question you could think of asking about this puzzle can be answered by looking at the diagram. And I can see two different ways to do it, right? One, so just to draw some paths, sorry to scribble on my picture, but you could go one way like that, or you could go like this, right? Those two paths would demonstrate, or they would represent two really different solutions to the puzzle. So here are two solutions. In terms of our language, a solution would be written as a string with the letters G, C, H, or N. And one solution going around sort of the lower arrow there would be G, N, H, G, C, N, G. I got that by looking at these letters here. G, N, H, G, C, N, G, right? Following the arrows, reading those letters gives me one string, which leads you from the start to the end. But I could have also done along the sort of the inner track. I could have done or G, N, and then C, G, H, N, G, right? And this is a different solution, but both are correct. All right. Are those the only two solutions, or are there yet more solutions?
Can't you use the reverse arrows to, like, kind of elongate your answer?
Yes. So your answer to this question, are there other solutions? Your answer should be sort of, those are the two good solutions, but there are other kind of stupid solutions. For example, you could do G, 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 N, H, G, C, N, G. What I just did was I went back and forth here a bunch of times and then did the usual trail to the end, right? That is also a legal solution, although it's sort of a stupid one. Or you could do a slightly less stupid but still fairly stupid answer would be to go, you could go around this little loop right here as many times as you like before finally continuing to the end of the puzzle. I don't know if you saw that. You could just keep on going around this loop because all these arrows are going forwards and backwards. There's no reason to do that in the real world. Of course, this is not a terribly realistic scenario in the real world anyway. But the whole point is, this diagram, once you have figured out what the diagram is, you can basically answer any question that anybody could ask you about the puzzle. The diagram contains all the information about it. And in a sense, the diagram is sort of like the proper way to analyze this puzzle. All right, any questions about that? In the same way, we can use similar diagrams. I will say, I'm not actually going to do another big example like this, but similar analysis could work for other kinds of puzzles or games or something. For any, I would say, finite, no chance game or puzzle. For example, something like tic-tac-toe, you could draw a state diagram which describes all possible tic-tac-toe games, right? You start with the empty board. In the first move, the person could go in the middle, or they could go up top, or they could go in the corner. Let's just say those are the only three possibilities. Other possibilities would be some kind of symmetric version of those same boards. And then each of these has several moves that the other player could take. But anyway, you could, in theory, just write out all possible configurations of moves on a tic-tac-toe board in a giant DFA. And then if you're actually playing tic-tac-toe, you could use this giant diagram as reference and basically win every time, or at least tie every time, because that's how tic-tac-toe works, right? Or you could do something, or maybe something like a Rubik's Cube. Like a Rubik's Cube puzzle also has only finitely many possible configurations it could be in, right? And it has a very specific, like, goal configuration that you want to get to, right? So, I mean, you would never really do this in reality, but you could, in theory, write down a giant state diagram where every possible configuration of the cube was one state. Now, there's many. There's a huge number of possible configurations, but then each arrow would be one of the possible moves that you can make, and if you want to solve the puzzle, you just find where you are in the diagram and you look for a path that goes to the final state. Or even something like, even something like chess. Like, in theory, chess is very complicated, but in theory there are only finitely many possible configurations of a chessboard, and only finitely many ways that the pieces could be arranged. And you could just determine which of those lead to winning configurations. Again, you wouldn't really want to do this, and even with a computer, this is not a good way to analyze chess by computer because there are too many configurations. But I'm just trying to say this way of thinking about things is a very powerful kind of general approach to lots of different scenarios. Any questions about that? That's all I want to say about that for now. All right, let's get back to some more specific, sort of smaller examples, more like the ones that we are typically going to focus on. So far, we have been constructing DFAs in the sense of, like, I say, and the homework questions are like this. I give you a particular language or set of strings, and I say, tell me what the DFA is that accepts these strings and rejects other strings. I want to try and think of it the other way around, though. What if I show you a DFA? I could ask you, which are the strings that are accepted and rejected by this DFA? So here's an example. Here's a DFA on this alphabet. My favorite, the two-letter alphabet here. Here is a DFA. This is another type of problem that we are going to have to get used to. Oops, sorry, I meant B here, A here, like this. I want to know which strings are accepted. Can you describe to me the set of strings which would be accepted on this machine and the set which would be rejected? I mean, I could just write some out. For example, the string A is accepted, right? Because if you want to do just A, you start in this state, you do A, which comes back to this state, and that's accepting, and so A would be accepted. Or AA or AAA, etc. All of those would be accepted if you just do, from the starting point, if you do A over and over again, it will be accepted, right? Anyone want to, can you shout out another string which also will be accepted but doesn't look like those?
B.
B? Yes. Because when I start here, I do B, and I end here, and that is accepted. Yeah. What else?
BB.
Yeah, so you can also do any power of B, etc. Anything else? Maybe that's it. Yeah, what'd you say?
What, AB?
Yeah, AB is also accepted because you start here, you do A, and then B. So that is also accepted. Would you agree if I said AAB? That means you go A, and then A again, and then B, right? Anybody have a feeling in general what will be accepted by this?
So it'll be A to the power of M, B to the power of M. So it doesn't matter, it has to be A and then any B. So any A and then followed by any B.
Yeah, so I think he said, oops, anything that looks like that. A bunch of A's followed by a bunch of B's, but that's it. All right? I think I agree. This, where can I ask a follow-up? The N and the M, can they be any number? Can they be 0? Or do they have to be...
It can be 0.
Yeah, possibly N and M are 0, right? You could have no A's there, in which case it's all B's, which we already said that would be accepted. So I'm going to say any A to the N, B to the M, where N and M are natural numbers. And in this class, this natural number includes 0. Sometimes this is something that mathematicians haven't quite decided on a standard. When people say natural numbers, sometimes it means they have 0, sometimes they don't. But in our textbook and in this class, natural numbers include 0 always. All right. So this one accepts anything that has A's followed by B's and nothing else. So in particular, the only thing that's not allowed here is an A after a B. Right? You can never have an A after a B for strings that are accepted by this machine. All right. So can I write? Sorry, I'm looking at my paper. I wrote something wrong on my paper. I don't know what I was thinking. Yeah. So anyway, this what I'm described here Oh, somebody just texted a question. I mean, chatted, not texted. Don't text me. You don't have my number. Someone chatted, why can't there be an A after a B? Because if we start, so on the diagram here, if you ever have an A after a B, that means at some point you did a B here, and then tried to do an A, you'd end up stuck forever in this rejecting state, right? These two states are the only ones which will accept. And so the only way, if you see a after a B, that's going to dump you into this state, which is a rejection. All right. Okay, so this we can write it as a set. The DFA accepts this set, A to the N, B to the N, M, such that N and M are in the natural numbers, right? This style of writing, this is what the book calls set former notation, and I hope that you're comfortable writing sets like this. So the bar in the middle, you know, a set is always written with these curly things. The bar in the middle you read as meaning something like such that. So this says it's the set of all strings that look like A to the N, B to the M, such that N and M are natural numbers. All right. This set, there's a name for that. This is called the language of the DFA. Remember, the word language just means any set of strings. I don't know if you remember from the first day we talked about a language, and an alphabet and a language. A language is any set of strings, and so that set, it certainly is a language. So this is called the language of the DFA. All right, or sometimes called the language accepted by the DFA for obvious reasons. Oftentimes we are going to give a name to our DFAs. So if the DFA is called M, I'm usually going to call him M for machine, then the language of M is written L of M. The language of M, right? So if you have a machine M, L of M means the set of all strings which are accepted by that machine. That's called the language of the machine, all right? And here's a definition. Certain languages, remember language just means a set of strings. Certain languages can be the language of a DFA, and there's a name for that. So I'm going to say if L is a language, and L is the language accepted by some DFA, then we say L is a regular language. All right. So regular language, it just means it is the language accepted by some DFA. All right. And the big question, which we're going to be asking for the first month or so, at least of the class, is just simply which languages are regular and which are not. Which languages are regular? And which are not. All right. We've seen several examples of DFAs already, and the language of any one of those is automatically a regular language. Somebody's asking me another question by the chat. You can feel free to interrupt me audibly, by the way, but the chat is fine too. Somebody asks, is it when I write something in this kind of set forming notation, is it possible to have like different ways to write the same set? And the answer is yes, that is definitely possible. So this notation is not ambiguous, but there are several ways you could write any given set can be expressed in in different ways. So when you're doing the homework, for instance, if you look up the answer in the back of the book and yours doesn't look exactly the same, that might be okay, because there are different ways you could write it. Right? All right. Okay. A big question is, which languages are regular? For example, a to the n, b to the n, and m in the natural numbers. This is regular, right? That's because I just showed you a DFA which has this as its language. All right. We just saw the DFA for this language, right? What other languages are regular? Well, we've seen several examples of DFAs. For example, the set a to the n, where n is even. This is regular, right? This is like on the first day, maybe, or the second day. We talked about this DFA. Must have been the second day. All right. Remember the language of that machine. This is a machine which accepts only even number of A's, right? And so you could write, oops, that in terms of a set is this, a to the power n, where n is even. All right. Here's another demonstration of what someone just asked. This is the same set, a to the power 2k, where k is any natural number, right? That's the same as saying that the exponent is even. I said it's wrote it as a multiple of 2. They look different, but they're the same set. All right, this is also a regular language. What about a to the 3n? Well, I'll write it the other way. A to the 3k, you could write n if you want. K in the natural numbers. This is also regular. We had an example like that where it accepts a string only if it has multiple of 3. The number of A's is a multiple of 3, right? Remember that one? It just went like this. Like that, right? So if I show you a set and I ask you, is it regular or not? What you have to do is create a DFA for it. And that's how you show that a language is regular, right? So to show some L language is regular, we must build a DFA for it. Right? That's how you demonstrate that a particular language is a regular language. You have to create a DFA which accepts that language. If you want to show that some language is not regular, that is much harder. So to show some L is not regular, and this we are going to discuss eventually, but we don't have real technique to do this yet. But we must, in this case, somehow, I'll say somehow, because this is really, it's not obvious how you would do this at all, but we must somehow argue that no possible DFA can accept L. And this, you should imagine, would require some kind of very, maybe abstract proof, right? If you want to show it is regular, all you have to do is draw the diagram of a DFA which accepts it. If you want to show it's not regular, you have to somehow logically explain why no possible diagram could ever have that as its language, that's not obvious at all how you would ever do that. Like I said, we are going to talk about techniques to do that, but that's kind of a big deal, which we're not going to get into right now. All right, but for example, I already told you actually there are some things that a DFA cannot do. For example, here's an example, a to the n such that n is prime. This is not regular. What I mean when I say that is no possible DFA can exist which accepts only, prime number exponents, all right? But I'm going to say this is hard to show. It's not obvious at all that that's not regular. And I think I said another example, some string on A's and B's where the number of A's is the same as the number of B's, that also is not a regular language. I said that a few times ago. So this question, I said today, a big question is, which languages are regular? I think last time I said one of the big questions that we wanted to ask is, like, what exactly are DFAs capable of computing? What kinds of sets can they compute? These questions are the same question, really, because regular means something which can be computed by a DFA. So the question of what are the capabilities of a DFA is really the same question as what kinds of languages are regular and which are not regular, because regular means it can be computed by a DFA. The whole, like, our point of view, or my sort of philosophical approach to thinking about this class is in terms of machines, particular machines. But actually, you could do the same topic. You could discuss always from the point of view of languages, because languages are related to machines in that we care about what kinds of languages can be produced by various different kinds of machines. So that's actually what our, the title of our book is called Formal Languages. And like, they don't use the word computation or machine in the title of the book, but they are talking about that. It's just they come at it from the point of view of languages. But really it's the same. All this business about computation is the same as, you can frame it all in terms of languages. All right? So these are big questions that we're going to get to eventually. Which languages are regular and which are not? I thought we would do one more fancy example. This is a fancy example, although it's not going to lead to a giant DFA like that other farmer puzzle thing. But one more fancy DFA. From the examples we've been doing so far, you might have the impression that DFAs are kind of abstract machines for doing very, very simple things. But this example is going to be about a much more kind of ordinary mathematical computation that you can do on a DFA. Let's use the alphabet consisting of just 0 and 1. And so, strings like 110, 11001, like that, right? All our strings will just be a bunch of zeros and ones stuck together. And I would like to make a DFA which does some kind of mathematical analysis of this string as if it were a binary number. So the strings are like this, and they are going to be interpreted as binary numbers. I don't know if you're into binary, but I will give you a very brief refresher about what I mean by binary numbers. So the way that we write down numbers is typically in what we call decimal. The DEC refers to base 10. Decimal numbers, they look like 0, 1, 2, 3, 4, 5, 6, 7. Maybe I'll just write down to 11 here. 8, 9, 10, 11. Okay, you can also write those numbers in binary. Binary is base 2 instead of base 10. Now, when I say we use base 10, what that means is you count up digits until you get to 9. But when you get to 10, there is no single digit for 10. When you get to 10, you carry over to the next digit and start again at 0. Right? That's what it means when we say we count in base 10. Binary is base 2. That means when you're writing numbers in binary, you never use the digit for 2. You only use 0 and 1. And when you get to 2, you carry over to the next digit. So the numbers written in binary go 0 first and then 1. But the next number, which in decimal I would write as 2. In binary, I carry it over to the next digit and write it like that. So it looks like 10, but it means 2 written in binary. All right. What's the next number? It's 11. You don't have to carry here. You just continue counting up. But from 11, I do have to carry in the rightmost position, right? So the right digit will carry over and become a 0. The next digit also will carry and become sort of a 10. So anyway, it's going to say 100 here. I hope I didn't line these up very well, did I? I don't know. I'm going to try and put in the lines here. It's my little binary chart. All right, let's just fill in the rest of these. After 100, of course, comes 101. After 101, I have to carry in the rightmost digit, and so it becomes like that. Next number is 111. That's a 7. And then I carry over all the way, and I get, oops, something like 1,000 here. And then I go 1001, 1010, 1011, etc. There's no reason to stop at 11, but I did enough. All right. This is how you write numbers in binary. And you know, why we use base 10? Why don't we count in binary? This is sort of a cultural issue. Like there is nothing mathematically special about base 10 numbers. It's just the way that human beings developed our language for numbers. We count in base 10, and most sort of anthropologists believe this because people have 10 fingers, and you know, most cultures around the world who developed number systems did so based on counting with their fingers. So we have 10 digits. Anyway, yes. Oh, you want to hear a stupid math joke? I firmly believe that all math jokes are stupid. But my stupid math joke about binary is there are 10 kinds of mathematicians. The ones who understand binary and the ones who don't. Get it? Yeah. 10 means 2 in binary. All right. Anyway, I would like for us to make a DFA. I don't know actually if we can do this in our remaining 3 minutes, but I'll describe the scenario at least. This sounds like a very complicated computation, but you can actually do what I'm about to say using a DFA. I would like to make a DFA which takes a binary string like this, zeros and ones, and accepts if the value is divisible by 3. That's how I want this DFA to work. It takes a string like this, and the string should be accepted if the value is divisible by 3, and should be rejected otherwise. Right? What seems interesting about this example to me is that actually if you ask me to do this, I don't really know how to tell you if a binary string is divisible by 3 or not, right? Is this number divisible by 3 or not in binary? Really, if you ask me this, the only way that I know how to do this is convert that number to decimal and then use some kind of knowledge that I have about which decimal numbers are divisible by 3, right? When I was a kid, I learned how to tell if a number is divisible by 2 or 5 or whatever. You know, there are tricks for that. Did any of you learn how to tell when you were a kid if a binary number is divisible by 3 or not? The answer is no, you didn't. There's no reason for you to have. And actually, I don't even know if there is a simple trick. But it turns out you can make a DFA which does this computation. And in fact, the DFA only requires a few states. It's not a very complicated DFA at all. This, like I said, this is meant to be an example of a DFA which actually does some kind of fairly sophisticated mathematical computation. So we've only got 1 more minute, so maybe I'll leave it at that, and then we will talk next time about how you actually make such a DFA. All right. I think that'll do it then. I'll see you all tomorrow. I'm gonna go snow blow the driveway.